In this video I want to explain the concept of a vector equation of a plane. So remember, a plane being a two-dimensional surface in three-dimensional space. And we're already familiar with these because we've solved systems of equations that relate to planes intersecting and thought about what types of intersections we can get. So I'm going to just pick an example of a Cartesian equation of a plane. And I've picked this one here, x minus y minus z equals -3, because I'm going to sort of show a graph of that one and how it behaves. So remember that explains a relationship between an infinite set of points x, y, and z. We can find an infinite set of values x, y, and z which will satisfy that equation. And if we were to graph all of those points in three-dimensional space, they would in fact form a plane surface. So here's three-dimensional axes, x, y, and z, and on there I'm just going to plot that equation. So there's the equation, there's the plane, whose equation is x minus y minus z equals -3. So that's kind of what it looks like if I move around there. And the reason it's got those edges is because they relate to the edge of this kind of box that it's sitting in. It's a 10 by 10 by 10 box, if you can see the scales on the axes. So those edges there just relate to where the edge of the box is, but of course in reality this extends out infinitely in every direction, that green surface. Alright, so let's think about some points that lie on that plane. Let's start with one particular point. So I've just picked the point with coordinates 1, 1, 3, and if you'd like to think about that for a moment, you could convince yourself that it does indeed satisfy the equation x minus y minus z equals -3. So that's a point, there it is, sitting on the plane, and there's an infinite number of those points. And what we want is a vector which not only describes that point, but describes every other point. So first of all, what about a vector describing that point? Well, there it is there, pointing from the origin up to the point with coordinates 1, 1, 3. But we obviously need a variable vector, so a vector which can describe every single point on that plane. And if I was to try and sort of show that, I could animate this vector moving around, and it's pointing to, can you see how it's sort of going up and pointing to all different points on that plane? Now the way it's animated, it's not pointing to every single point, but you can see that it's going across and pointing to quite a few of those. Alright, so we need a vector which is going to describe all of those, and notice it's a vector which is not at any point lying on the plane, so it's not kind of, parallel to the plane. At every point it's pointing from the origin there up to a point on the plane. So what we want is a way to express that vector. So let's come back here now, and I'll get rid of that specific example because we're going to talk a little bit more general. And to start off with, this might seem a little bit general and a little bit kind of hard to understand, but I'm going to think about some components that would allow us to define a vector. So first of all, let's think about what we're after. We're after a vector which will describe the location of every point on the plane. So I'm going to call P just a general point x, y, z, and so we'll say that R is the position vector of that point. Now I'll draw it that way so maybe it helps to look a little bit like it's kind of coming from underneath the plane. So the origin is sort of below and it's pointing upwards to that point P. So what would I need in order to be able to get a vector equation? Well, I'm going to suggest that if we had two other things, we could get a vector equation of the plane. So the first thing I would want is the specific coordinates of another point on the plane. So this, I should have said, is our vector r, which is the position vector of any point on the plane. That's our variable vector. And then we want the coordinates of a specific point somewhere on the plane. So we'll say that's the point A, which has position vector A. Then we could say that the vector joining A and P, so the vector AP or the vector PA, that is a vector which does lie on the plane, or sometimes we say in the plane. So that one actually is parallel, it's in the plane, it joins 2 points that are on the plane. So that would be helpful for us to have that. The other thing that would be helpful for us to have is actually a vector which is normal to the plane. So let me try and draw if we can picture n is a vector which is perpendicular to the plane. And it could be sort of pointing upwards out of the plane, it could be pointing down out of the plane. As long as it's at right angles to the plane, that's all we need. And so now we've got a vector on the plane and a vector perpendicular to the plane. And that means that, well, every vector that's on the plane somewhere here must be perpendicular to n, because n is perpendicular to the plane. So now we could make a statement saying the vector AP is perpendicular to the vector n, and that allows us to come up with a dot product expression that AP dot n is equal to the scalar value 0. So let's express AP in terms of the position vectors. Well, AP is the position vector of P minus the position vector of A. We know that's true for the vector joining any 2 points. So then we get R minus A dot n equals 0, and if we expand our dot product, we get R dot n minus A dot n equals 0. And to go one step further, we could say R dot n equals A dot n. Now, that is not in the form R equals something. So we're not getting a vector equation like we do with a line, where we've got R equals some, varying vector based on a parameter. But what we do have is we're saying if we take the dot product of R, so in other words the position vector of any point on the plane, the dot product of it with any vector normal to the plane, it will be equal to that scalar product A dot n, which will just be a constant because A will have specific values and n will have specific values. That'll just be a constant. Alright, now I'm going to put a little box around that because that, in fact, as potentially unsatisfying as it seems, that is the vector equation of a plane that we have on our formula sheet. So we'll need to understand how to use that. Now before we go and do an example, I'm going to just relate that to the Cartesian equation. So I'm going to say let's let the vector n actually have components A for its I component, B for its J component, and C for its K component. And so we can say then that the vector equation of the plane, which is of this form here, is going to be, well, R is the position vector of the point which has coordinates x, y, z. So as a vector it is x, y, z, xi, yj, zk. N is a, b, c. And a dot n, well, a dot n is going to end up being a constant. So I'll write a dot n there. Let's complete these dot products. So we've got a times x plus b times y plus c times z equals, let's say, equals k, where k is equal to a dot n. I've just noticed in the line above that I've written dot there, and that should be equals. Alright, so there we have the Cartesian equation of, or that we're sort of familiar with, isn't it? Something times x, something times y, something times z equals a constant. Now, to get it in the form that it is on the formula sheet, we just need to bring the constant across to the same side as the other terms. And because we're doing that, we'll call it d instead of k. So I guess d in this case is really the negative of a dot n, isn't it? So that's the Cartesian equation for a plane that we have. That's not what I want. Cartesian equation for a plane that we have on our formula sheet. So that's, should I put here that d is equal to the negative of a dot n. Now at this stage we're probably still a little bit unsatisfied with that equation and exactly what it means. Just to show that it is what we have on our formula sheet. There it is there. So the vector equation of a plane and the Cartesian equation of a plane. And if we want to understand the relationship between those two, we just need to remember that the x and the y and the z come from the r vector. So that's the general point, any point on the plane with coordinates x, y, z. And then the a, b, and c are the components of the vector n. So I'll finish this video here, and then in the next video I'll do an example where we might actually find the vector equation of a plane.